Okay, so let's talk about some properties of the image. And they have very similar properties, but the proof and explanation is very different. So before we dive into those properties, let's talk about what the image of A is. So the image of A is going to be a set of all vectors x such that there is a y with ay equal to x. So just give an overview of what this means. This is a set. Right? This says the image is a set of all x such that this holds. And let's just take a minute to appreciate what this condition says here on the right. This condition says that the image is the set of all outputs. The only way to have a vector be an output is if there's something that you input, necessarily a y, that gives you that output. So unlike before, we can't just plug in x and expect to follow through and show that something's in the image. We have to find a vector that is an input that gives us that. So let's go through our first fun fact here about the image. And these are going to be replicate of what we had before. So the zero vector is always in the image of A. Doesn't matter what A is. Regardless of what matrix we have, the zero vector is always going to be in the image of A. And so what we need to do is we need to find a y with ay equal to the zero vector. So this is the goal. Whenever we want to show something's in the image, we have to show that something can be put into that transformation that we can multiply by that matrix A to give us the zero vector. All right. So the full explanation is that we're going to try y equals 0. We're going to try the zero vector. Right. So just for emphasis, we started with this. We started with the zero vector, and our key, we need to pick a key that makes this work. So the fact that the key and the start are the same thing, the fact that x and y are the same thing, is kind of very special to this case. And it's even more special because we have no idea what A is, but we do know that regardless of what A is, if we multiply A times the zero vector, we get out the zero vector. So that checks out. We wanted to check if the zero vector was in the image, and the certificate, the key to open that door, was to find the y that worked. And it's a coincidence that these are in fact the same. So that tells us that 0 is always in the image. So if you want to think about this geometrically, we can build this picture where the image of A is always going to at least contain that point, that origin. And just like what we did beforehand at the start, the image is not necessarily, right? The image can just be that origin, just like in this example right here. So the image doesn't need to be more than a point, but at least you start with a point. You start with a point, and that point has to be the origin. All right, so what are the other facts? These facts are going to be just like we had before. So if we have two vectors, x1 and x2, are in the image, then so is x1 plus x2. All right, so why is this? So let's just start with the given, right? The given is that x1 and x2 are in the image. So whenever you want to reason something out, you should think about, okay, what do I know? And then you should ask yourself, what does that really mean? If you're in the image, this means we have a y. In this case, we're going to be specific and call it y1, where that vector is times A gives us our vector X. So we started, right? If I start with X1, I said, I want to ask the question, is X1 in the image? Can I get it out on this graph? If I know it's in the image, there's some input, there's some key that I can put into that gives me out my X1. That's what being in the image means. And likewise, we have for Y2, for X2 rather, we have an X2 such that when you multiply that by A, you get X2. And these two are just properties of being in the image. The definition of the image is that if you are in the image, that means there is some Y. If you are in the image, if I know that X is in the set, I tell you it's in the set. That means this holds. There is a Y. We have no idea what it is. So this may seem very strange because we have no idea what A is. We have no idea what X is. But if we know that X is in the image, we know at the very minimum, it has this property that there's a corresponding Y. If you want to think of this in terms of inputs and outputs, if we know X1 and X2 are both possible outputs of the matrix transformation A, then we know that each of those has a corresponding input. And that corresponding input is Y1 and Y2. All right, and the goal in this case is we want to show that X1 plus X2 is also in the image. All right, and what does this really mean? This means that there is some Y such that A times Y is equal to X1 plus X2. We don't know what this Y is. This Y is going to be a big question mark. But we just need to find some vector that works such that when we multiply it by A, we get X1 plus X2. All right, so let's start our explanation. We're going to start with our givens. So we can start with these two properties. So we know that there is some Y such that AY gives us X1. And we're going to also use this other one. So we're going to use these two. These are going to be our starting points. And now what we're going to do is we're just going to add these equations together. We're going to add these together. And what do we get? We get AY1 plus AY2 is equal to X1 plus X2. All right, so now we kind of have our output. We have our goal. We still don't have that Y quite yet. But we can get there if we factor that A. If we factor A in, what do we get on the left? We get that A times Y1 plus Y2 is equal to X1 plus X2. And now we've reached our goal. Our goal was to find some Y such that AY. So this right here, the Y1 plus Y2, that right there is our Y. We had no idea what that was going to look like, but that's our Y. And so what this says is, if we have two things in the image, two vectors in the image, the sum has to be 2. So to go back similar to the kernel, what does it say? That we started with our origin, but if I know that I have a vector, and I know I have another vector, then this is going to start forming some grid. It's going to start forming a grid. And so the shape of the image has to be very smooth. It has to be a point or a line or a plane or a hyperplane, but it can't be any funny shape. Once you get two vectors in your image, you can always get out the sum of them. All right, let's just do one more. Let's do the other one just to see if you can do it. So if X1 is in the image, then K times X1 is 2. And so this follows exactly the same idea as before, but now we only have one vector. So the given is that we know that X1 is in the image. We know that X1, the vector X1 is in the image. And what this really means is there is a Y. There is some input, Y, we'll call it Y1, such that A times Y1 gives us out X. And the goal of that we want to do is we want to show that K times X1 is in the image. But what does this really mean? this really means that there's a y. That y could be different, but there's a y such that ay is equal times k times x. Oops. K times x1. There we go. All right, and so similar to before, we're going to take our equation that we know is true. This is something we know. We're going to start here, and now we're going to multiply both sides by k. So we multiply both sides by k. We get kay1 equals kx1. And now we're almost done, right? We have our goal here on the right. We have a k times x1 here on the right. But we don't have a times something, so we're going to factor in that. We're going to factor in that k. And so altogether we have a times ky1 equals kx1. So what this means is if I have a vector in my image, if we go back up to this picture that we drew before, if I have some vector in the image, say that red vector, then I can take any scalar multiple of it. I can go backwards, I can take twice as long, I can go backwards 15 times. And so this really makes this into this grid. And the image is then going to be a linear combination of all these different vectors. So geometrically, it's going to be a line, a plane, or a hyperplane. And algebraically, it's going to be a set that's a linear combination of vectors. So that's what this really means. So here we're done because we found the y. Here's the y right here. That's our y that we wanted. And so we're done. And so we can put these together like before. I'm not going to go through the details. But we also know that if you have two vectors x1 and x2 in the image of A, then you can take any linear combination of them. And so this idea here really solidifies that what the image or kernel looks like, all these fun facts that we've done today, they're going to look like things like this. They're going to be some combination of vectors. Right, I'm just making up some numbers. So algebraically, we're going to be able to write the image and kernel like this. Some linear combination of vectors in what looks like geometric vector form. Right, maybe more generally, you might think of it like this. Right, some combination of vectors. And geometrically, they're always going to be either a point or a line. So they might be a point, they might be a line, they might be a hyperplane. So if you take this in a higher dimensional space, you may get, a very complicated shape. It could be a plane. If you do this in 3 dimensions, right, it's going to look something like this. It's going to be a very smooth object to begin with. So this is kind of the prototypical example of what we're going to keep studying are different shapes that can generate these lines, planes, and hyperplanes. And algebraically, they're going to be things that come in this linear combination or geometric vector form.